Our first run through the material of this course, when we talked about the material we're talking about today last, we were focused on how to understand expressions that have exponents in them where those exponents are not whole numbers. Right? How do you somehow multiply a number by itself 1.5 times? Right? That was the kind of question we wrestled with last time we saw this material. So let's just use that as our starting point to get our heads back in the game. If I'm going to evaluate 16 to the power 3 halves, how in the world do I do that? How do I raise the number 16 to a power 3 over 2, 1.5? That's not a whole number. What if I change, yeah, go ahead. Let's solve a simpler problem, classic problem-solving technique. We don't remember how to solve this slightly complex problem. What if I change this fraction from 3 halves to 1 half instead? Does that ring any more bells?
Then it would be 16 to the power of 8.
So, on the one hand, and this is one of the common areas to kind of, if your brain isn't thinking in that analytical mode, which it's really effortful to get our brains to think about math in a very detailed analytical fashion. We have to intently think about it for a minute. If we're not there yet, we can confuse this problem with 16 times 1 half, which would be 8. But we don't have 16 times 1 half, we have 16 to the power 1 half.
Square root of 16.
So last time we met fractional exponents. We use the properties of how exponents work with one another, how they combine with one another, to justify why raising a number to the 1 half power is the same thing as taking its square root. That's the definition, and that's true no matter what the base of your exponential expression is. If the exponent is 1 half, then it's the same thing as a square root. So maybe a mantra for this work is that fractional exponents are roots. We can't evaluate an exponential expression with a fraction up there without thinking about roots. Fractional exponents are roots. And how did we know, by the way, that this was a square root? Why is square root the right root to use here? Where is that square idea coming from? What makes this a square root is that the denominator of this fraction is a 2. Right? And the denominator of the fraction becomes what we call the index of the radical, which we don't usually write the index of the radical for a square root, but if we did, we would do that by sneaking a little 2 into the crook of this radical. Right? So the denominator becomes the index of that radical. What is the square root of 16? 4. Because 4 squared is equal to 16. Okay, great. So if that's how to raise a number to the 1 half power, then how do we raise a number to the 3 halves power, going back to the original problem? What do you think? So what we need to figure out how this relates to the problem that we just did. Right? Since we know how to deal with the 1 half power, if we can relate this to the 1 half power in a way that's easy, then we should be able to solve it. And the way to do that is to break apart the 3 halves from up here. Break it apart into 3 times 1 half. So this is really, or maybe better yet, 1 half times 3. After all, 1 half times 3 is 3 halves. Right? But then multiplying exponents is the same thing as raising a power to a power. That was one of the key properties of exponents that we looked at in the first run through the course. So I can rewrite this as 16 to the 1 half raised to the power 3. But that's useful because we know what 16 to the power 1 half is. What is 16 to the power 1 half? It's 4. So really, 16 to the 3 halves is the same thing as 4 to the power 3. And 4 to the power 3 is 64. 4 times 4 times 4. The first pair give me a 16, and then multiply that by 4 again, gives me 64. Right? So this is what the true meaning of having a fraction and an exponent is, right? Is that the denominator of that fraction tells me that I need to take a root with the index equal to that denominator of the base. And then if there's a numerator that's not 1, as there was in this example, right, then I can raise that result to that numerator power, and then I get my answer. Right? So having a fraction in an exponent means that we're in this roots and radicals land. The key property that we're going to need for today in all of this, if you know sort of nothing else about roots, the thing to know about them, besides the fact that they're fractional exponents, related to the fact that they're fractional exponents, because they are fractional exponents, that means that they can, and in fact their definition is that they do, is that they undo powers. Let me just talk a little bit more about what that means. Let's focus in on this relationship here one more time. The square root of 16 is equal to 4. So that establishes, the way I like to think about it, it establishes a relationship between the number 16 and the number 4. But that relationship goes two ways. On the one hand, going from left to right, we have this square root operation. It says if I apply the square root to the number 16, the result is the number 4. So the square root of 16 is 4. What does this relationship look like in the other direction? If 16 is related to 4 by 4 being the square root of 16, how is 16 related to 4 going the other way? I'm not posing this question maybe very accurately. Or maybe another way to say it is, what's another relationship between the numbers 4 and 16 that explains the same thing that this equation does? Maybe I'm still not saying it well, so let me say it one more time in a way that I've already said it earlier. Why is the square root of 16 equal to 4? Because 4 times 4 is 16, and I'm going to write 4 times 4 here as 4 squared. Yes, exactly. So the relationship going the other direction is the squaring relationship, right? Raising a number to the second power. Okay. So 4 raised to the second power is equal to 16. And, at the same time, the square root of 16 is equal to 4. So both of those equations are describing the same relationship between the numbers 4 and 16. They're just describing it in the opposite direction. Right? And for that reason, taking a square root and squaring are opposite. They're inverse operations to one another, sort of like multiplication and division or addition and subtraction. Whatever one of them does, the other one can undo. That's the takeaway here. Which means that now roots and radicals are going to give us the tools to either get rid of a square in an equation, if I need to, within limits, or, and what we're going to talk about today, is in the other direction. We can get rid of square roots in an equation by doing this. So if I have an equation with a square root in it, I can get rid of the square root, which will be useful for solving to get the variable by itself, by applying the squaring operator. So let's start with the example in problem number 2 here. So here I have an equation that tells me that v is some number whose square root is equal to 10. How should I solve this equation to get the v by itself? Exactly. So according to what we were saying a minute ago, if I square both sides, then on the left-hand side, I'm going to end up with the square root of v, the quantity squared. I'm going to write that like this. And then on the right-hand side, I'm going to have 10 squared. And 10 squared is, what is 10 squared? 100. It's 10 times 10. So, let me just recopy the left-hand side here one more time. Square root of v, the quantity squared. But then that's equal to 100. But then, how do we understand what is the square root of v squared? Given that the square root and the square are inverse operations to one another, what happens over here? The fact that they are inverse means exactly that they cancel one another out. Just like addition and subtraction cancel one another out, multiplication and division cancel one another out. Taking the square of a square root cancels both of those operations out. So the square goes away, the radical goes away, and the v is by itself, which is, after all, the whole point of solving an equation, right? To get that variable by itself. So what's the takeaway here? What are you going to want to remember about this example? So the takeaway is that if one side of my equation is the square root of a quantity, then I can get rid of that square root by squaring both sides. And once I've squared both sides, the square and the square root, because they're inverse to one another, annihilate and leave me just with the quantity that was underneath the square root sign. We call it the radicand, but we don't need to know that.